he doesn't have the logs don't match, right? It came back online.
I just followed that.
But did you go one behind trying to see them, or did you select?
Yes, they have optimization where it's like you have this term
Where you match?
where you match and get something like
Yeah.
and then you say,
Right.
what's it called? There's this is a match index.
How does it restrict RPC? I think there's 20 RPCs for PhDs.
I don't know the exact qualification for it, but I just know that essentially they
So complicated. Like you have to redo the test to understand what it wants.
I didn't do that.
Yeah.
Yeah, that's what I did. So I did the.
Let's get started. So we've already finished everything before at the very bottom layer of the database. So basically, we talk about disk space management, buffer management, and file and access method before this lecture. And starting from this lecture, we will go into the details of how we actually implement query evaluation and optimization, I would say SQL part, how the database actually implement the SQL process language, and how do the database actually optimize the execution of queries. So let's first review a little bit about the simplest query you could come up with, the single table parts. So basically, the basic form of a single table query is like this. So you have a select, a target list, the column or the column expression list, and you have a from clause which specifies which table you are selecting data from. And so suppose we only have, we just have the minimal SQL query, which is select something from something, and we apply a where clause as a filter on the actual data. So basically, this query gives you all the students whose department is CS, and we select the name and GPA for those students, right? So that's probably the simplest query you could come up with. So the processing of this is actually straightforward, even if you do not understand a bit about how database actually execute queries or optimize queries. The way you do that is basically you scan. So basically, the students is a table. So it's in a heap file, which consists of a bunch of tuples in this students table. So the way you do that is you scan everything there. You scan all the tuples in that particular heap file and apply the filter to each of the tuple you're reading on the fly, right? So basically, for each of the tuple, you read the column department, then compare that with the string CS. If it's a match, then you extract the name and GPA columns of this tuple and output that to, say, string or a network or a file, right? So that's basically the basic flow of the simplest possible SQL query. What if we add a distinct, right? If we add a distinct, then we must do a deduplication over the results, right? So we have a bunch of name and GPA pairs, right? So even if you in the students table you don't have duplicate records for one student, but you still could end up with students with the same name and the same GPA in the end, right? It just happens. So suppose you want to do a distinct on that. Or what's making more sense to me is probably in this students table you might have duplicate student records. Okay, so one possibility is that maybe in this particular table, if a student changes his major, okay, his or her major, then you add a new record for that and assign a new ID. Maybe that's the case. Okay, then you could end up with duplicate name and GPA pairs for one student, but one is for before he or she made the major change. The other one is after, right? That's also one possibility why you want to do this thing. So how do we actually do this thing? So now you have a bunch of name and GPA pairs, and you want to remove all the duplicates, right? So basically, you could do sorting, right? Once you sort everything based on name and GPA, then you can just do a linear scan to remove the duplicates. Or you could use a hash table. Whenever you have the next output, you probe that hash table to see if the output has already appeared in your output screen. If that's the case, then you just ignore the current output and continue with the next one. Okay, then those are two options. Basically, this is not. So this is just a basic like intuition of how you would do that. So don't mind if you are having trouble following all the details, because we will talk about everything again later in this lecture. Okay, so that's distinct. Then the next thing you could add is you can add a sorting on top of the results. So basically, you might want to sort the result by GPA first, by name, the lexicographical order of the name. Then finally, by 2 times the age. That's all. It could be something you might want to do, right? So if you want to do this sorting, basically, so if your output size is small, then you do internal sorting, like quick sort. If your output size is huge, so that it doesn't fit in memory, then probably you need to dump those to disk and then do external sorting, right? That's what we talked about in the last lecture. Okay. So basically, in the order by clause, everything must refer to columns in output, right? So if something is not in output, then you cannot sort by that, of course, right? So and also you could use the alias you set in the select target, like you could do s.h times 2 as a2. Name s.h times 2 as assign an alias for that as a2. Then you can do order by a2 for that, right? And also you could also specify whether you would do ascending order or descending order. That's basically in this case the higher GPA the tuple will appear like before others, like tuples with higher GPA will appear before the tuple with lower GPAs, and that's basically DESC, descending. And if two tuples have the same GPA, then you order them by the ascending order of name. Okay, so that's basically the normal lexicographical order by comparing the letters. If the first unmatched letter, so if the first unmatched letter of the first tuple is smaller than the first unmatched letter of the second tuple, then it's placed before the first one is placed before the second one in the lexicographical order. Okay, so that's ascending. So basically, you can mix and match all the descending and ascending spec here. Yeah. And on top of that, you could also do an average. So if you just put, you don't, so now we still don't have the group by, okay? So if we just put the average there, then basically you only have one column, one row. Okay, so you basically add everything up. In this case, you're computing the average of that specific column. So in this case, even if you add distinct, that doesn't make sense because you only have one row. And also, it doesn't make sense to have an order by because you only have one row, right? So if you have a single aggregate, then this is probably the query you might want to write. It doesn't make sense to add distinct or order by. And so, how you do that is basically you could materialize everything, materialize all the outputs and aggregate them on top of the output, or you could do this on the fly, right? You could, when you are scanning a file and whenever there's a match of the department to CS, you maintain a count and the sum of s.gpa, and in the end you output the sum divided by the count, right? So that's basically the implementation of the average. You could also use distinct inside the bracket. Okay, so that's basically so you could add a distinct here. So you could add a distinct here. What does that mean? That basically means you are gonna only average the distinct value of GPAs. Okay. Suppose two guys have a GPA of 4, one guy has a GPA of 3, then the average would be, it's not 4 plus 4 plus 3 divided by 3. That's the result of average as GPA. Okay. So suppose your GPA column is like this. So basically you have 4, 4, 3. Okay. Then for average of distinct as GPA, this is going to be 4 plus 3 over 2. Okay. So basically you do a distinct before you actually do the aggregate. Okay. That's the use of distinct. And then the next thing you could add is the group by clause, right? You could group the students by their department and compute the average for each of the department. Okay. So basically, you have to somehow group your pupils with the same department value into small groups and place the average operator on top of that. So basically, this query will produce one row for each of the group. In particular, here for each of the departments that's existent in your table, then there will be one output for that, and that consists of the name of the department and the average GPA of the students in that department. Okay. So you could also add a having. Having basically contrary to the where clause. The where clause applies to the tuples you are scanning on the base table, or like here on the student table. The having clause applies to the groups. Okay, your final result. So basically, you could do whatever the previous mentioned procedure to get a bunch of groups. Then you apply the having filter on top of the groups. So suppose here we have a count star greater than 5. Then implicitly you're basically assuming you have 2 aggregates for each group instead of 1, right? Because you have to count how many students there are in that department. But although it's not in the final output you're requesting, but you have to compute that. So basically here, for each of the group, you maintain the name of the group and the average student GPA in that group and count how many students there are in the group. Then finally, once you get all the groups, you do a filtering on the groups so that only those with at least 6 students is selected, right? So the having is basically the last, placed on top of the output of a select group. Select group by property. Then finally, putting all together, you get the most complex, the most complicated single table query you could end up with. So in a way to do that, basically you scan the student's table, do the filtering s.gender equal to f, as you find all the female students. Then you apply the group by. Basically group the female students by their by their department. Then you request the output of like when you are maintaining the groups, you maintain for each group you record the department name and maintain the average of GPA and also do a count of the number of female students in that department. Once you do that, you place the having clause on top of the output. Basically, you apply the filter count star greater than 5 to the groups, to the output groups. So you only retain those groups with at least 5 female students. Then finally, you do the order by. That's the last step of your query processing. So basically, you sort everything by the department name and output the results. So that's basically the most complex single table query you could come up with. Okay, any questions so far? That's just a review of everything we talked about in the first couple of lectures. Okay. So next we will really go into the details of query processing. So let's first give you basically an overview of the flow of query processing. So how do we actually do that? So remember, in a real database system, basically, this is a layered approach. So the upper level will only need to care about its own logic. And so basically, for query processing, it will not handle things like how do you actually format the tuples, how do you actually format the pages, or how do you allocate pages or allocate free spaces on the pages or on the disk, or how do you allocate memory buffer frame? How do you allocate a memory buffer frame for query processing? So basically, it just calls into different components to get those functionalities done. So if the query processing part wants to access, say, a tuple on a page, so basically you can just call into the buffer frame, the buffer pool, ask the buffer pool to fetch the page, ping the page into one of the buffer frame. So if the page is not in memory, then basically the buffer pool in turn calls into the disk space management or the disk space management part to fetch the page into memory. Then once that's done, the buffer pool returns the page to the upper level of query processing. So basically, the key intuition here is that for query processing, it doesn't need to care about how to allocate the page or how to actually fetch the page, how to make sure a page is in memory. So it just calls some routines in other components of the database. But what the query processing really cares about is, given these primitive operations like get a page, read a tuple, read a value out of tuple, how does it how it can actually execute the queries, how it can actually optimize the query, because for each of the query you might have multiple possible ways of executing that. Each have different trade-offs, like in memory consumption, disk space consumption, or running time, right? So how it actually choose one of the best according to a criteria, right? Also, there might, since this is a skyline problem. That's basically saying you have multiple objectives, right? So if your goal is to minimize the memory footprint, then the best plan might not be running as fast as if you have enough memory, right? So how do you make trade-off between them? That's the problem of query optimizer. Okay. And so finally, that's basically the goal of query processing. And then how do we actually implement that? So the query, so basically we have the query optimizer is step before the actual query execution. It translates the SQL into a special internal language called query plan. So you can think of a query plan as a tree, I would say. Typically, if you do not have recursive sequence, then it's a tree. Right, it's a tree. And then, so this tree might just look like a bunch of operators, and it basically represents a data flow. You can imagine, so let's see the example, okay? So suppose we have this query, select distinct name and GPA from students. Then you could come up with this plan. Suppose the optimizer produces this plan. So basically, it's basically the same we talked before. To do this query, you do a heap scan first. This is at the bottom, you have a heap scan here. So you have a heap scan. So basically, the heap scan produces all the tuples in the students table. Then for each of the tuple, you can think of this the lines as a pipeline. That's something like a pipe, okay, like water pipe. The tuples basically flows through the water pipes, okay, just like water from bottom up. Okay, so once your heap scan operator produces a tuple, is sent to the sort operator. Then potentially, if this is a non-blocking operator, then it could just in turn send that to the distinct operator. However, as you know, the sorting is actually a blocking operator, right? So why is that? It cannot just send everything on the fly, right? Because when you're producing tuples and you want everything in a sorted order, you cannot decide what's the smallest item until you have all the tuples, right? So that's why the sorting is actually a blocking operator, which we will talk about later. So the key things here happens about the sort is that for the sort, it will maintain a large, maybe a memory buffer, right? A private buffer. And once your heap scan operator sends a tuple to the sort, it just stores the tuple inside that buffer. Okay, so it accumulates the tuples in that buffer. So basically, here in a square, so you have a bunch of tuples. Then suppose your tuples fit in memory, then this is fine. Once your heap scan stops, tells the sort operator that I'm done. I'm finished with all the tuples in your students table. Then the sort decides, I can start sorting the student tuples, right? So here, because you are just doing a name and GPA, so basically you can just sort that based on the primary key, which may not necessarily be the name and GPA here, right? Because you are basically just deduplicating the tuples. Two tuples are the same if and only if all the values in all the columns matches, right? All the values in all the columns match. So for a table with primary keys, that basically reduces to the problem of matching the primary keys, right? So if two tuples have the same primary key, then they are duplicate because the primary key decides the remainder of the other columns. So on the other hand, two tuples, if they are not the same, then their primary key will not be the same, right? So basically, you can just sort the students table based on the primary key, maybe not shown here, but like student ID. Finally, what you do is you do a distinct operator. So here, the distinct operator is actually a non-blocking operator. Why is that? Because you have a sorted range of items. Say you have a bunch of 1, 1, 2, 2, 2, 3, right? So the way you do that is you always produce the first item. Then for each of the items in the string, you compare that with the previous one. Okay. So suppose you have produced the first tuple, and you're going to examine the second tuple produced by the sort. Suppose since this is 1, it has the same value as the previous one, so it's a duplicate, right? So you just basically skip that tuple and continue with the next one, 2. And since 2 is different from the previous one, it's a new item. The reason that why this is correct is that your range is sorted, right? If your range is not sorted, then it could be a bunch of like 2s, then the key grows smaller, like a bunch of 1s. Then you could also still have a bunch of 2s after that. This is not sorted. So basically, the distinct operator will not work on unsorted data because, since it's not sorted, you cannot guarantee that if your item is not the same as the previous one, it could also have some duplicates far behind in the history, right? So for the 2 here, you do not, since for this 2 here, it's not the same as the first tuple 1, right? These 2 are not the same, but since the data is not sorted, there could be some matching tuples far behind in the history, right? So that's basically the distinct operator must apply to a sort operator. Okay, so that's the general idea of or the general model of product processing. So this is just an intuitive way to describe this. This is just like you have a, so I would say the lines here is, as I said, is like a water pipe. Okay, so your tuple is basically water, right? It can flow through along the line from bottom to up. However, there could be some like the source is a blocking operator. It's something like a pool. Okay, your water must flow into that pool first, and so it's like a swimming pool. So basically, you have 2 pipes. One pipe is for ingesting, like pouring the water into the pool. Then the other is for draining the water from the pool, right? So the sorting operator is just like that. You basically pour the water from heap scan into sort and pull every tuples there into the swimming pool. Then you close you turn off the input. Then you turn on the draining tap, right? And the water basically starts flowing to the next stop, this state. So that's how the the blocking operator works. Like if you have a non-blocking operator like the distinct here, whenever you some water flows through here, it doesn't have any like pool for that. Basically, it's just like a knob in your water pipe system, right? Whenever some water flows through, you might just do some processing over that, then like direct the water into the next one. Okay. So that's the analogy for the data, like the data flow model. So in reality, how do we actually implement this in programming languages? So basically, for each of the relational operator, in fact, this is not exactly the same, the correct way to say that. Actually, it's for each of the relational operator and each of the physical operator. Okay, so we will discuss we would like define what is a physical operator later, but it's basically you can think of that as some kind of actual operation you might want to do on top of the data, right? Like the heap scan here, it's a physical operator instead of just a relational operator. So in relational algebra, we just have join, projection, like selection, right? So those are like abstraction of how the semantics of your code. But in reality, you also have some other operators that actually helps implement your semantics, like heap scan, right? You don't have a heap scan in relational algebra, but you do have that in your database system to like read data from the disk, right? So that's the distinction between relational and physical operator. But anyway, so for all the operator, you can think of that as having as an iterator interface or the iterator concept in C++, right? So basically, you could have a bunch of methods in this iterator class. So each of your operator extends or inherits this iterator class. So each of the operator will implement its own version of this methods here. Like you could have input init initialization, right? So initially you need to initialize some internal states, like for the sorting, you need to initialize a large memory pool, right? Then the next thing is called next. Okay. So this next here, basically the tuple. The tuple is also a class, right? You can think of that as a class. So since the next returns the next, basically once you call that, it will return the next tuple that's produced by this iterator. Okay. So it could also be null, right? So suppose you when you call next, you don't have the next tuple, then basically return null to signal that. And the close is basically for cleaning up. So once you finish all the processing in your system, like in your database system, you finish all the processing for a particular query, you need to clean up the states maintained by these iterators. Like for sorting, you need to deallocate the large memory pool to just allocate it for storing the tuples flow from the heap scan, right? So that's the purpose of the close. And finally, you have a bunch of iterators, the inputs iterators here. They are basically the downstream, or I would say upstream. Yeah, I would say upstream. So basically, since the tuples from bottom to up, I would say the bottom is the upstream and the top is the downstream. Okay, because the tuples from bottom up. Then these iterators are basically the iterators for the upstream operators. Okay, that's a little bit confusing. It's basically, so suppose we have a sort, right? So in the sort, so suppose this iterator for sort is called sort iterator. Anyway, so suppose you have a sort iterator, then the input here is basically, so suppose this is the previous example, the input here is basically an abstract iterator of the heap scan. Okay, so basically this is of the type of heap scan iterator. Okay. But the reason that we only use the abstract type or interface in the definition is actually any of your iterator could be applied to different upstream iterators, right? Or operators, right? So suppose you have a sorting operator. As long as your upstream operator still implement the same iterator interface, the sorting operator will apply to that particular upstream operator. An example is that, so as you see in the previous example, your sorting your sorting operator applies to the heap scan, right? Basically, you read everything from your heap and do a sort over that. That's the implementation of this sort. But you could also apply the very same logic to the output of an index scan. Right? It could be scanning, say, a B plus tree. and produce a bunch of tuples out there. Then probably you could also do a sorting over those tuples generated from an index scan instead of a heap scan. Okay? So that's why you do not want to write a specific type for these iterators. Otherwise, you have to create one particular version of your operator for each of the possible upstream operators. That's too complicated. So, right. Just a side note. So basically, this model, as we said, it's a data flow. It's a data flow model, or in a more familiar, it has a more familiar name to the database community. It's called a volcano model. Okay, volcano is something that you can erupt, right? So it's like your upstream operators starts erupting, and those things that pops out of these operators are the tuples. Then it gets pushed up, like all the way to the top. Okay, that's why it's called a volcano model. Volcano model, right? So that's more familiar. If you talk about this kind of data flow diagram to the database, people they will tell you, oh, hey, this is a classic or traditional volcano model. That's what they do. So yeah, let's see a very real example of how we actually implement one of the operators. So suppose here we implement the distinct operator using the operator interface. So how do we actually implement that? So suppose this distinct only applies to sorting data. Okay, so not necessarily. We could also apply that to cache. Anyway, so suppose we have a distinct operator, and of course we will have the very same interfaces as specified in the previous slide. We have init, next, and close, right? And for a distinct operator, you only have one input. That's basically a sorted string. Or as we can see later, you could also do a hash-based distinct. That's basically you do a group by first, then you do the distinct. So this input here has a length of 1 because you only have one input for the distinct operator, and it could be either a sort or a group by. Right? And then finally, you have this column and value. Right? This is just a very simple example. This is doing deduplication over one single column. Okay, you can only store one column ID. You only have one value in the previous value. So that's a oversimplified version of this distinct operator. So in a real database system, basically you will have an array of, instead of that, you will have an array of column IDs. And your values will consist of two instead of one value. Okay? Then you could do a multi-column deduplication. But for here, for simplicity, we just talk about one column, a single column deduplication operator. Okay? So the way you actually implement this, as you can imagine, so basically during initialization, you have to initialize the child first. Okay? You always initialize the child first. That is because the child is the child operator, like the inputs, is not related to its the downstream operators. Okay, so if you produce some kind of tuples in the volcano model, you can send that to whatever downstream iterator is calling you, right? So we can just do any combination. Like if you have a heap scan, it doesn't have to consider whether its downstream is a sort or just a deduplication or output, right? Or a projection. It doesn't matter. It just blindly sends the output to that particular downstream operator. So basically in the volcano model, the upstream operator are agnostic to the downstream operators. So that's why in the init, you always initialize the child input first. Okay. So in reality, actually, the call to initialize that is done to. So as you can see, this is a slightly non-realistic way of implementing this operator because here you don't have right. So in reality, how do you actually initialize the value to your iterator, right? So if you imagine this in Java, how do you create a new object for that particular input if you don't know the type of that? Right? So in reality, actually, that comes from a plan, right? A plan just looks like the diagram, the data flow diagram we've shown before, except that it's planned instead of the iterators. Okay, so basically it has the very same structure. You will have a bunch of plan nodes. Something could be called like heap scan operator, right? Then you have a sort operator. Sort operator. Then you have what's that? Distinct, right? Distinct operator. And these are basically the plan nodes. Then, when you are initializing everything, you directly map each of the nodes into an iterator and establish your links through the input. Okay? So basically, for here, you can do that from bottom up. From the heap scan operator, you create a heap scan iterator. Okay? These are the iterators. In some places, it is also called like something like execution nodes, or it could also be called physical operator. Okay. Those are different names, just different names. But basically, the idea is from a description of this operator, you create an iterator. So basically here, out of the heap scan operator, you create a heap scan iterator. Then you create a sort iterator out of the sort operator. And you link that to the inputs value. So basically you set the inputs of your source iterator to the heap scan iterator. Okay. That's how you do that. Then finally, for the distinct operator, you create distinct iterator. Okay, and then again, the input of this distinct iterator is sent to the upstream of iterator, which is sort iterator. Okay, that's how you actually initialize the fields here. And also, you are also gonna initialize other internal states. No, actually not. So basically, internal states are initialized by the recursive call of init, but something are not internal states, like here, right? Like the column ID and the previous value. Previous value is the internal state, but the column ID, it's not something. It's not something that comes from your runtime, right? It's not populated during runtime. Instead, this piece of information, like the column ID here, it comes from your query, right? In your query, if you are doing distinct on top of like name, then this is the column ID of the name. That actually comes from, so here, it comes from the operator itself. In the operator, you record what column ID you're basically doing deduplication over. And then you basically copy that column ID to the distinct iterator so that it knows what column you might want to do the duplication on. Then finally, the way you actually initialize the internal states is to call the init method on the very top iterator. Okay, that's the very downstream iterator. Okay, in this case, that's the iterator that actually produces the final result. Here it is the distinct iterator. Okay, so once you call the init, as we said, you first, or you always first initialize the child input, right? So if you do this in Java, then basically every function in Java they don't say virtual function, but essentially it's a virtual function, right? Your function call is going to be directed. So although you're calling on top of an abstract interface called iterator, but the call is actually directed to the actual implementing class, right? So in this case, once you call the inputs 0, so once you call inputs 0 dot init, what happens is that like in Java or in C++, basically it's a virtual function table. Sorry, a virtual function table. Okay, so it will point to the correct version of your function, and since your upstream your child input or your upstream input is actually a sort, so this init call will be directed to the init method in your sort iterator, okay? And that's automatically handled by your program language, so that you don't have to worry about it. That's the key benefits of abstraction. Then once you finish once you land in the init method of your sort iterator, you will in turn cause the initialization of its upstream, its heap scan, right? So for the key point here is that for the distinct iterator, you do not have to worry about how its child initialize their states. Okay? So basically, you just call init on your inputs there, then you don't have to worry about anything about your child. That's the key point, right? So once you finish that, you initialize yourselves internal state. Like here in the distinct, it's basically you initialize the pre value to null, right? Because you have not seen anything at this point. So basically, anything that compares to null is not equal, right? So that means basically you will always produce the first record, which is correct. That's init. The way you actually implement next, you can think of that. That's whenever you call next, your iterator should return the next tuple in your output, and then maybe you change your state so that you are ready to produce the next after the next, right? And it could also be that you have depleted all your outputs, then you return null, right? So the way you do that for the distinct, as we said, the distinct is a non-blocking operator. Basically, you can just look at the current one and the previous one. So you remember the previous one and compare the current one with the previous one. If they equal, then you just return the current one, right? And if the current one, if the current one is not equal to the previous one, then you return the current one because it's not a duplicate. But if the current one equals to the previous one, then it's a duplicate. So you don't actually return that. You repeatedly fetch the next tuple from your child, and until you find one that doesn't compare equal to the previous one. Okay? So that's basically the flow here. So first you call next on inputs 1, inputs 0, right? Since in almost all every programming language except maybe MATLAB, Octave, and maybe Pascal, the array index starts from 0. Right? So you should put a 0 here. So when you call next on input 0, you get the current tuple from your child. Then what you do is that if the next returns EOF or null, right? Basically that indicates you have reached the end of your file or reached the end of your string. Then that means basically you don't have the next. Then what you do is you basically just return EOF to pure downstream. Okay. So in this case, since the distinct is the final operator in your data, in your data flow diagram, once it returns EOF, that indicates you are depleted all your output. And then if the next call on the input 0 is not EOF, then you do have the next or the current tuple. What you do is you extract the column with column ID of the current tuple and compare that value to your previous value. Okay. So if they match, then that means this is a duplicate. Then you just skip this one and loop back. You start from the first line. Okay, so this loop starts from the first line. Or if they don't match, then that means this is not a duplicate. Then you should return this tuple. But before you return, you have to remember the value of the current tuple so that the next one can compare against this one, right? So you update the previous value to the column to the value of the column with column ID of the current tuple, and then you can just return the current tuple. Okay, that's basically the flow of the next method of the distinct iterator. Then finally, when you are finished with everything with the query, you call close on distinct, right? So I would say in reality you should swap these two methods. Okay, you should always clean your internal states first. Then typically, I would say just typically, just in case if you come up with something weird, typically you do this first. You release any dynamically allocated memory in your iterator. Okay. In this case, this is the previous value because for each of the previous value, you could, if you have ever seen any tuple from your child, then you should have allocated some character array for the previous value, right? So that's some dynamic memory you've allocated. So you should deallocate that, right, in close. Then once you do that, you should call close on the child input, right? So that the child input will have a chance to clean up its state. And then you're done. Yeah.
What's your reasoning for calling close on the child after?
Okay, so so what really can happen is that so in reality, remember this is a character star, right? It's a pointer. So in reality, you don't actually copy tuples across the iterators. You just pass pointers. So it could be the case that this pointer belongs to your child iterator. It could be an internal state in that, right? If that's the case, you do not want to deallocate you do not want to deallocate that memory here. Okay, you should in turn deallocate that memory. Rely on the close method of your child iterator to deallocate that memory. And that still doesn't explain why the second one should happen first, right? So that's because sometimes you have some dependency of deallocation. Okay, suppose some of your deallocation actually relies on one of the values in your previous, in your child. Okay, let me think about it. Yeah, one notable example would be. Yeah, so suppose you have a counter in your chart, okay? That indicates how many groups you have, and then you have some aggregates for each of the group, and then each of the aggregate structure is a dynamically allocated structure, right? So you have to iterate through everything there to deallocate these aggregate structures. But how do you know how many groups you have? That actually comes from the child iterator, right? So if you deallocate the child iterator first, then you lose the information about how many loops you have, right? So then you are unable to actually deallocate the memory of your own internal state. Right? That's because of the dependency. Why the other way is not true is because, as I said, the child iterator should be agnostic to what iterator its downstream is, right? So the child cannot actually depend on this iterator. So that's why you should always, typically, I would say just typically, you should always release your own internal state first, then call the close on the child. But of course, there are exceptions because the real SQL is really nasty. You could have some mutually dependent operators. You could also have like the most obvious example is recursive SQL. Okay, if you know what recursive SQL is, that's basically your previous right. So basically, your current batch of results depends on the previous batch of results, right? So yeah, you could have some mutual dependency in that case. So that's something you need to be careful about. So yeah. But anyway, in a typical simplistic model, this is fine. Okay. More questions about the distinct operator? Okay, that's basically the implementation of that. So in SimpleDB, in the project tree, you are basically going to implement a whole bunch of operators. That's what you're going to do. You are not actually going to implement the optimizer. Instead, you are just going to implement the individual operators in this model. Okay. Of course, the method names are different, but they have the same concept. Okay. Yeah. So let's talk a little bit more about group by operator. Okay. So one possible way of doing group by is use sorting. Okay. So once you sort data by its group by column, it's implicitly group by, right? So it's the same. It's roughly the same thing as your previous distinct operator. Whenever you have the next operator in your sorted array, you compare that with the previous one, right? If they have matching values, then they're in the same group. Otherwise, they are not. You create a new group for that. So that's the sort group by. It's really easy. But the key things to know here is basically sort is a blocking operator. That's one thing, right? So that means you have to buffer all the inputs before you actually do the group by and any aggregation on top of that. Why is that a problem? Actually, so this is okay for this is okay for extremely large data and extremely small data. Why is that? For extremely small data, this is totally fine because it is fast anyway. Whatever you do is fast. You can just do like a nested loop, right? It's also going to be fast. If your data is only like 10 items, right? N squared doesn't make too much overhead here. Or if this is extremely large data, this is also okay, because as we said, external sorting is fast. Right? External sorting only takes a log number of passes, and each pass is basically a scan of your whole data. Given your data is so large, they cannot fit in memory, you have to do multiple passes anyway, right? So that's also okay. But the case that this is not okay is like you have a moderately large data, okay? It could be very close to your memory limit, or it exceeds your memory limit, okay? So if it's really close to your memory limit, the reason you might not want to do that is because the internal sorting is not cheap as well, right? Although it's cheaper than IO, but it's not cheap as well. It's an involved. So, and especially if you have a really, really huge memory, like 512 gigabytes in your box, it's more than likely you have a NUMA structure, right? NUMA is basically you have multiple sockets. Each socket is installed with a CPU, and then you have different memory controllers which have different latencies to different regions of your 512 gigabytes of memory, right? So it could be the case that you have 512 gigabytes of memory. Half of them is faster to access on the left, on the CPU 0, and the second half is faster to access on CPU 1, right? Those could be the case. So if you just blindly like put data into your memory, so that it occupies most of this 512 gigabytes of memory, then once you start doing the the group sort, what happens is that whenever you do that partition, it's likely you are swapping tuples, one from the first half of your memory and one from the second half of your memory. And this is significantly slower than if you just do that in one region, right? So of course, some care needs to be taken for a Newman data structure. But anyway, a general relational database should work on whatever machine that you provide me, right? So if you have a really, so suppose I just don't know the details of that, and I somehow accidentally installed the relational database that just blindly put everything into memory. Then what happens is that you can expect a sudden decrease in performance once you are using half of your memory, right? Or like maybe 3/4 of your memory. Okay. And that's gonna be weird because you will think, so if you don't know about NUMA, you will think, hey, I have memory, why is this performance drop? It doesn't make sense, right? So that's something the database system has to take into consideration. So for NUMA, of course, you have better way to utilize that, but just for the traditional relational database, what you could do is actually you can maybe set a threshold of the maximum memory you could use. Then once beyond that, you start switching to a better algorithm. Okay. So yeah, that's about the sorting. Right. So what's the alternative to sorting? You can also use a hash table, right? Or a hash index. You can imagine. So this hash index is actually not prebuilt. Unlike it's not like the B+3 you build in your system, like using a created index. It's something that you build on the fly. Okay. So once your tuple flows through from the heap scan operator to your group by operator, or in this case, it's actually a hash, and yeah, a hash. So if you will look like something like a heap scan, like something like a hash, then you do a hash group by, or alternatively, this could also be called hash aggregation, something like that, because the group by is typically almost certainly followed by an aggregation, so it could also be called hash aggregation, something like that. So this hash basically computes the hash value for each of the tuples on the line and attach that hash value to the tuple. Then, in the hash aggregation, basically you build a hash table, right? And so since here we are maintaining aggregates, the hash table doesn't have to actually keep every tuple. You can just maintain those aggregates on the fly, right? And this is better than the previous approach, because in the previous approach, you have to keep all the tuples before you actually do the aggregation, right? Here, you are just tossing out the tuples. Instead, you just maintain a summary of them. So that means basically, given the same memory budget, you are going to be able to handle more groups, even purely in memory for that, right? So that's one good thing about this. Also, still, you could still end up with larger data sets so that you have more groups than the memory can hold, right? So what you do in that case? Then the general idea is basically you use a 2-level of hashing. Okay, it's not something like the perfect hashing we mentioned before. This is more practical and less I would say theoretical, or I mean, that's not actually really realistic. But here, this is a realistic idea. So basically, you use two hash functions. The first hash function partition the data into small regions, and you dump those regions onto disk. Okay, so you end up with a bunch of partitions, each of which potentially could fit in memory. Right? So it's something like this. In the first phase, you use a partition hash function and partition the. So suppose you have still m over b main memory buffers, then you could partition the original data into m over b minus 1 partitions. Okay, you only need still this is the same, roughly the same model as we use for external sorting, except it is hashed. Okay, so for every page, from your input like key file, you read that into your memory and produce a tuple to your hashing, right? So for your hashing, you compute the hash value using the hash function HP, the partitioning hash function, and put that tuple into one of the buckets, right? And then whenever your buffer frame for that bucket fills up, you dump that to disk. Okay, so finally you end up with a bunch of blocks or partitions, right? The property of these partitions is that every tuple in the same partition has the same value given using the partitioning hash function HP. Okay, so basically everything here has the same value. Say they all have the same hash value of 1. These guys all have the same hash value of 2, and so on, right? And then how do you group by, right? So since for a single group, everything in that have matching value in the group by columns. So that in turn means whatever hash function you use, they will have the same value, right? So that means everything in a single group will be in the same partition, right? So basically, you can expect one will contain every thing for each of the group that actually appears in this partition, right? But it doesn't necessarily mean partition 1 we have one group, right? You could have different keys mapped to the same partition in the first phase, right? So what you do in the next phase is you create a second level hash function for each of these partitions. So you process each of the partitions one at a time. Okay. So basically that means you bring every page in the first partition into memory and build a hash table using a second hash function HR. Remember this HR should be different from HP, and usually you require them to have some kind of nice properties so that the hash value assigned by HR is totally independent from HP. Okay, that's where this two-wise independent might come into play, right? So basically, the key thing is basically HR could assign totally different hash values to each of the groups in your first partition instead of the hash value 1. Then you just build a in-memory hash table for those tuples, right? And still, this is since if everything like if your partition 1 has if your partition 1 has a fewer number of pages than the size of the memory buffer, like if partition 1, so suppose the number of pages of partition 1 is smaller than or equal to m over b, then the thing you could do is basically you can just put everything into the memory, right? And build a hash table that compute the aggregates. Even better, actually this might be a little bit weird. So this is not always the case, right? This is not the essential requirement for that. Why is that? Because since this time everything fits in memory, you can handle more groups because for each group you only maintain aggregate instead of the actual tuples, right? So actually, this can be relaxed as long as your value of your groups. So suppose the size of your value of groups is k, and your aggregate has a size of a, right? And then you can fit, you can fit this many of groups in memory, right? But anyway, that's just an optimization you could do, right? Okay, so let's do some analysis about this approach. So suppose we do not apply the final optimization we talked about, like we do not try to maintain, or even if we try to maintain the aggregate on the fly for the second level hashing, we still are not sure whether they can fit in memory or not, right? So for safety or to be safe, but basically we can still just assume in the second level we require each of the partitions to be smaller than or equal to m over b pages, right? So then, how big a table can be if we just want to do like one pass? One pass is basically you do one repartition and then do reading the partition and do your rehashing again. Okay, that's one pass. So how big a table can be if we want to do everything in one pass as we described before? So remember in phase 1, we have m over b minus 1 spatial partitions, right? They are the number of partitions after the first phase. Then for the second phase, you require each of the partition to have a size no larger than m over b pages here, right? So what's the total size? It's suppose everything is the largest, which is the largest possible size. Then you end up with m over b times m over b minus 1 pages in your original table, right? So said differently, that means you can hash a table of size So you can hash a table of right. Sorry, 1 second. Something goes wrong here. Right. So, here I don't see anything on my screen, so I cannot write on the slides. Close it. Alright, works. Okay. So basically let's continue. So said differently, we can hash a table of size n over b in about square root of n over b pages in memory. Okay. The reason is that m over b times m over b minus 1 needs to be so that's the largest size of the data of your table. So that means n over b needs to be smaller than or equal to that number. And the second one, since your memory buffer pool is typically large, we can just approximate that by n over b squared, right? So if you do that, basically that means n over b, m over b is greater than or equal to the square root of n over b, right? So that means if you have said that in the reverse direction, is that if you have a file of n over b pages, the smallest memory you need for one pass hashing is basically square root of this n over b, right? So of course, in reality, things will not go very smoothly if you do this because each of the buckets could, some of the buckets could have more tuples than average, and some could have less, right? But with a typical, I would say, if you assume the data is benign, by benign I mean it follows like a uniform distribution. You might have some variance, but not too large. Then you can add a small buffer to that square root of n over b. Then you're fine. You typically can do that in one pass, right? Okay. Anyway, that of course that still doesn't sound right, right? So that means if you do unfortunately end up with a larger partition than your memory, well, what you do is you have to do another pass in that small partition, right? You have to recursively do that, okay? So, right. Yeah, I don't have a slide anyway. So let's go back to, to this. Suppose, like here, for the second partition, you actually have more than m over b pages. So what can you do is actually you can apply a second pass to repartition this partition. Okay, that's a different function, hash function than HP. Let's call it HP prime. Say we call it HP prime. It's gonna be partition this partition 2 into smaller partitions, like m over b minus 1 smaller partitions. Then those will on top of that we apply the HR, the rehash function, to bring those small smaller partitions one at a time into memory and do the aggregation. Okay, that's how you do that. But however, still that's not that's not ideal, right? So if your partition is just slightly larger than optimal, which happens really rarely, and you do not want to pay that many of cost just for a bunch of so suppose your memory buffer has 10,000 pages, and you just overflow by 1 page. You don't want to pay the full cost of reading 1,001 pages in, writing 1,001 pages out for repartitioning, and read them in again for the final step, right? So you could use this approach. We can do better using something called hybrid hashing. Okay. So for the hybrid hashing, I would say if you can understand the notation here, that's good. But I would say it's a much simpler idea than what seems here. Okay. This is just for the formality of mathematics, so that doesn't matter. The real intuition here is that you maintain a k in-memory hash table of size k. It has k pages. Okay. So when you do this, where's that? Okay. So HH is actually the same as the partition function we used before. Okay. So this is for partition. If the partition hash function returns a hash code of 0, that's basically this is the first bucket. Then you directly put that tuple into this in-memory hash table using the HR, the rehash, the second hash. Okay, so that means basically if your entire data can fit in the k page memory in-memory hash table, then basically you do not need to do any additional I/O in writing out the partitions or bringing the partitions again, right? You can directly maintain an in-memory hash table for that. But if, unfortunately, your data is slightly larger than that, or significantly larger than that, you still have the chance to do the normal, multi-pass hashing, like partitioning them into smaller chunks, then bringing one chunk at a time to do the hashing, right? And you can actually apply this at every step. When you are bringing the external memory on disk, the partitions on disks back into memory to build a hash table, you could also apply this, right? You could also create a in-memory hash table of reasonable size, but still maintain a bunch of partitions just in case if your that doesn't fit in memory. Yes.
The in-memory hash table, that's just the hash table of the summaries, right?
Right. This is just a hash table of summaries.
So you have lots of.
Right. It's a lot smaller than those partitions. Okay. So that's why this will work really well in practice. Okay. So then the whole flow of your algorithm is basically you apply hybrid hashing to your entire data set, and if you do not end up with any partition on disk, then you're done. If you do have some partitions on this, then you apply that again on each of the partitions until you do not have any partitions on this. So that's how it happens. Alright, so I guess that's about this lecture. We will talk about other stuff next. Okay, so
Yeah, that's how I was doing the presentation. Too. I know the state. Yeah, it's
right. So
like my
Yeah, so my 2A has 19.
right. So basically, you want to hash.
Sometimes it won't pass.
yeah, I got it. So I can run 100 processes at the same time.
But if you guys all the same, if you guys
So 2A solve that, so let's say the 2B, right?
Right?
So-
Yeah, really like the block.
Particles from different groups that put in the same
So get left.
you
Yeah,
cannot
nice.
distribute some part of that.
because I want to start writing it. So I want to know which architecture we are going to do so that at least I just get some point out.
Right. So basically, this part will have actual triples.
No,
Okay, so these guys will
write a report like this.
another space. But here you will have
so
some
description of the problem. Why do you think?
not the description of the same pattern. So these are for
So for this part, I'm asking which architecture are you going to stay?
these are those that doesn't so basically everything here is from some groups and everything here is from some other groups that doesn't fit.
Okay, then I didn't become proposed to.
We'll actually go over this at the end because we have to talk about the details, right? The real details about this. We'll go over this again next time.
Just seemed like that's what you were doing.
Yeah. That what I feel is just intuition. So that's just the surface of understanding. But we'll go over this again.